The 11. The diamond ceiling. Part 4. The liquid ceiling. Data centers, gallium, and the end of the chiller. A documentary script. 33 minutes by Richard C.J. Young. Sejong. Continuation of the cross-sector thermal unification thesis. Act 1. The wall returns. In part 1 of this documentary, we named a wall. Heat. The universal constraint on industrial civilization. We followed it through 5 sectors. The power grid that derates on hot days. The electrolyzer that eats its own electrodes. The solar cell that burns its own collector. The laser that distorts its own beam. The battery that must outlive the maintenance window. 5 industries. 1 wall. 1 solution beginning to emerge from a laboratory in Houston. We did not, in that first film, walk inside the building where the wall is thickest. We did not enter the data center. We enter it now. A modern hyperscale AI data center is not a building that houses computers. It is a thermal engine that happens to compute. The latest generation of AI accelerator chips dissipate between 700 and 1,000 watts each. The generation arriving by 2028 will dissipate over 1,200. A single rack, holding a few dozen of these chips, draws between 80 and 120 kilowatts of electrical power. Nearly all of that power becomes heat. The computation is the byproduct. The heat is the product. The building exists to move the heat somewhere else. Of the enormous electrical draw of a modern AI data center, roughly 40%, nearly half, is consumed not by computation, but by the systems that remove the heat the computation generates. Industrial chillers, massive air handlers, liquid cooling loops, pump stations, cooling towers. The facility spends almost as much energy fighting the consequence of its own process as it spends performing the process. The wall has a price tag, and inside the data center, the price tag is larger than anywhere else on Earth. The cooling infrastructure is not a footnote. It is the dominant cost. The chillers, the pumps, the raised floors, the secondary water loops, the fan walls. This is the machinery that a hyperscale facility actually pays for. The chips are expensive. The building that keeps the chips alive is more expensive. And the building is getting more expensive every year because the chips are getting hotter every year. This is where we return to the wall. Because the same thermal ceiling that limits the power grid, the electrolyzer, the solar cell, and the laser, the same wall, runs straight through the server rack. And the material that Part 1 identified as the means to crack that wall, diamond, is already arriving inside the data center. But it arrives alone. It handles the first millimeter. It does not handle the next meter. For that, we need a second material. And that material is a liquid metal. Act 2. The fluid that cannot serve the flux, the standard cooling fluid inside a direct-to-chip liquid loop, is water. Water is the default. It is cheap. It is safe. It is well understood. It has a thermal conductivity of roughly 0.6 watts per meter per Kelvin. It has a volumetric heat capacity of 4.1 heat megajoules per cubic meter per Kelvin. It is the reference fluid against which every alternative is measured. For the chips that defined the last decade of computing, water is sufficient. A 300-watt processor, cooled by a copper cold plate with water flowing through microchannels at a few liters per minute, reaches a stable operating temperature with a manageable thermal gradient. The system works. It is the incumbent. It is technology readiness level 9, fully commercial, the default hyperscale standard. The problem is the next chip, not the chip in the rack today. The chip arriving in 2028 and beyond. The chip that dissipates 1,200 watts. The chip that, in a 4x4 centimeter footprint, generates a heat flux that water cannot physically evacuate through a microchannel of any practical dimension. The bottleneck is not the water's heat capacity. Water can absorb the energy. The bottleneck is the rate at which the heat crosses the boundary from the solid into the fluid. That rate is governed by the fluid's thermal conductivity and its volumetric thermal capacity. How much energy a given volume of the fluid can carry per degree of temperature rise, and how fast that energy moves through the fluid by conduction rather than by bulk flow. Water's thermal conductivity is 0.6 K. Its volumetric heat capacity is 4.18 mJ nm/K. These numbers are fixed by the physics of liquid water. They are not engineering problems. They are properties of the molecule. Liquid gallium and its practical eutectic alloy, Galinstan, a mixture of gallium, indium, and tin that remains liquid below room temperature, has a thermal conductivity of roughly 16 to 29 watts per meter per Kelvin, depending on alloy composition. That is roughly 27 to 48 times the conductivity of water. Its volumetric thermal capacity is approximately 25.8 megajoules per cubic meter per Kelvin, over 6 times that of water. These numbers mean something physical. They mean that a given volume of liquid gallium can carry more heat per degree of temperature rise, and can move that heat through itself by conduction faster than the same volume of water by a factor that is not marginal. It is an order of magnitude. At the heat flux of a 1,100 watt accelerator, water can still carry the energy, but you need more of it. Larger channels, higher flow rates, bigger pumps, and a larger temperature gradient across the boundary. The cold plate grows. The plumbing grows. The pump power grows. The system does not break. It bloats. And the cost of the bloat, the larger cold plates, the higher flow pumps, the heavier structural supports, the more aggressive facility-side heat rejection, is what makes water at that flux economically marginal. Gallium does not bloat. A gallium microchannel can be smaller, run slower, and still move the same heat, because the fluid itself conducts the energy away from the wall faster than water can. The physical envelope of the cooling hardware shrinks. This is the advantage. Not that gallium is cheaper. It is not cheaper. It is that gallium fits inside the envelope that water has outgrown. This is the first honest statement of the thesis. Gallium is not a cheaper fluid. It is a denser thermal medium. It competes on flux, not on dollars. Act 3. The oxide front. If gallium were simply a better thermal fluid with no complications, it would already be inside every data center. It is not. The reason it is not is that it is, in engineering terms, one of the most chemically aggressive substances you can pump through a metal pipe. Gallium attacks aluminum. It attacks it instantly. At room temperature, liquid gallium diffuses into the grain boundaries of aluminum and causes liquid metal embrittlement, a catastrophic loss of structural integrity that can reduce a structural aluminum component to a crumbling, brittle mass within minutes. Aluminum is in every rack frame, every heat sink fin, every cold plate manifold, and every structural bracket in the current hyperscale supply chain. Raw aluminum cannot exist anywhere inside a gallium fluid loop. Not at a flange, not at a fitting, not at a seal. The loop must be hermetically isolated from every aluminum surface it could ever contact. Gallium attacks copper more slowly, but it attacks it. Copper and gallium form intermetallic compounds, copper-gallium 2, that dissolve the copper surface, thin the cold plate channel walls, and create localized cavitation erosion under high flow velocities. A copper cold plate in a gallium loop does not fail in minutes the way aluminum does. It fails in months. That is not a maintenance window a hyperscaler can accept. The wetted surfaces of a gallium loop must therefore be something other than aluminum or copper. The industry standard is a physical vapor deposition barrier, a layer 50 to 100 nanometers thick of tantalum or tungsten, deposited onto the interior of the cold plate, the channel walls, and every fitting that touches the fluid. Tantalum and tungsten are thermodynamically inert to gallium. They form an absolute barrier. No migration, no dissolution, no embrittlement. The fluid never touches the structural metal. It only ever touches the barrier. There is a second problem. It is the one the sales pitch does not mention. Gallium, on contact with trace oxygen, forms gallium oxide, Ga2O3, a nanometer-thin passivating skin. In a static thermal interface, this oxide is harmless. It is even useful. It stabilizes the surface. But in a dynamic, flowing loop, the oxide is a rheological disaster. The oxide skin is viscous. As the fluid moves, the skin is sheared, torn, and reformed, and the fragments of oxide suspended in the fluid transform it from a clean Newtonian liquid into a non-Newtonian sludge. The apparent viscosity of an oxidized gallium loop can spike by a factor of 10 to 20. The fluid that was supposed to flow like water now flows like wet cement. Inside an electromagnetic pump, the magnetohydrodynamic Lorentz force pump that is the entire silent, solid-state, no-moving parts selling point of the gallium architecture, the oxide is not merely a viscosity problem. It is an electrical problem. Gallium oxide is an electrical insulator. The suspended oxide flakes degrade the bulk electrical conductivity of the liquid metal stream. The Lorentz force that drives the fluid depends on that conductivity. As the oxide accumulates, countercurrent loops form inside the channel. Parasitic Hartmann layers develop along the walls. The magnetic drive that was supposed to move the fluid silently and without contact begins to fight itself. The velocity at the channel walls drops towards zero. The flow chokes. This is the live front. The mitigation is real engineering, not hand-waving. The loop must be hermetically sealed, welded stainless or ceramic joints, precision compressed Viton or metal C-rings, no elastomeric seals that allow oxygen permeation. Before filling, the channels are washed with hydrochloric acid or anhydrous ethanol to strip native oxides. Reservoirs are positively pressurized with ultra-pure nitrogen or argon so that any seal deflection pulls inert gas into the system rather than ambient air. The cold plate interiors are tantalum or tungsten. The microchannel housings are alumina or silicon nitride structural ceramics. This is not a fluid you pour into a copper pipe. This is a fluid that requires a hermetic, ceramic-lined, tantalum-barriered, magnetically pumped, inert, gas-blanketed closed loop that never, at any point in its operational life, contacts air or aluminum. The engineering is solvable. It is not simple, and it is not built yet. Act 4. The integrated stack. We now have two materials. Diamond, which solves the first millimeter. The hotspot at the die. Gallium, which solves the next meter. The transport of the heat out of the rack. The question is the boundary between them. The boundary is where thermal architectures usually fail. It is where the Part 1 grid story failed, where the copper-to-diamond interface cracked under thermal cycling. The boundary is the recurring villain of this entire documentary. The conventional approach would be to bond a copper microchannel cold plate to the back of a diamond heat spreader using a traditional thermal interface material, an indium solder, a thermal grease, a sintered silver paste. This introduces a thermal bottleneck at exactly the point where the heat flux is highest. The heat has just left the die, spread laterally across the diamond, and now must cross a mechanical joint into a copper substrate before entering the fluid. Every interface is a resistance. Every joint is a potential failure point. The integrated architecture does not do this. It eliminates the joint. In the integrated stack, the diamond is not a component bolted to a cold plate. The diamond is the cold plate. Or more precisely, the diamond is the structural floor of the microchannel. The liquid gallium flows directly over the back surface of the diamond. There is no copper. There is no indium solder. There is no thermal interface material. The heat leaves the die, enters the diamond, spreads laterally, and crosses directly into the fluid that will carry it away. To make this work, the diamond's wetted surface must be prepared. Pristine bulk diamond is chemically inert to gallium. Gallium will not dissolve it. But CVD diamond, as grown, is not pristine. It contains grain boundaries, amorphous carbon phases, and microscopic void defects from the plasma growth process. Liquid gallium, given access to those microfissures, will enter them by capillary action and cause subsurface delamination over time. The diamond surface must be sealed. The seal is a physical vapor deposition layer of tantalum or tungsten, 50 to 100 nanometers thick, applied to the diamond's wetted surface. This layer does two things. It provides an atomically smooth, high surface energy surface that liquid gallium wets flawlessly. The fluid contacts the barrier, not the diamond defects. And it is an absolute thermodynamic shield. No gallium atom reaches the underlying diamond matrix. No infiltration occurs. No delamination is possible. The microchannel walls themselves, the structure that contains the flowing gallium above the diamond, are micro-machined from structural ceramics, alumina, aluminum oxide, or silicon nitride. Gallium cannot wet or dissolve these non-metallic oxide and nitride networks. They are the ideal channel housing. The ceramic channel framework is bonded to the diamond using direct oxide bonding or transient liquid phase bonding, processes that leave the polished diamond back surface exposed inside the fluid channel, with the tantalum or tungsten barrier in place, ready for the gallium to wet. The thermal boundary conductance at this interface, the rate at which heat crosses from the diamond into the gallium, is the number that determines whether the integrated stack is a real architecture or a laboratory curiosity. The measurement for a diamond to gallium interface with a tantalum or tungsten barrier is between 120 and 180 megawatts per square meter per Kelvin. Compare this to the alternatives. A diamond to water interface in a direct microchannel has a thermal boundary conductance of 25 to 45 mA/K. The vast disparity in acoustic impedance between the rigid covalent bonds of the diamond crystal and the loosely bound molecules of liquid water creates a thermal boundary wall, a phonon vibration mismatch. The heat struggles to cross. A diamond to copper interface bonded with indium solder has a thermal boundary conductance of 40 to 70 mA/K. Solid-state acoustic mismatch. Again, diamond phonons versus copper lattice vibrations, with additional resistance if voids form in the solder. The diamond to gallium interface with the barrier is 2 to 7 times better than either. The mechanism is not phonon to phonon coupling. It is phonon to electron. The heat moves from the phonons of the diamond crystal into the electron cloud of the tantalum or tungsten barrier, and then directly into the dense electron sea of the molten gallium. The thermal transition is efficient because the electrons, not the lattice, carry it. The boundary that defeats water and copper does not defeat gallium. This is the integrated stack. The diamond is the spreader. The tantalum is the barrier. The gallium is the transport. The ceramic is the channel. The electromagnetic pump is the mover. There are no mechanical bearings. There are no impellers. There is no copper cold plate. There is no thermal interface material. The architecture is solid state at the chip and liquid metal at the rack, with a single high conductance boundary between them that does not bottleneck. Act 5. The 2033 cost crossover. The integrated stack works thermally. The question that determines whether it is built is whether it works economically. The single chip cooling stack, the diamond substrate, the tantalum barrier, the gallium charge, the ceramic microchannel, the MHD pump magnets, is expensive. A traditional premium copper and water cold plate costs roughly $350 per chip. The diamond gallium stack, at mid-2026 diamond prices, costs more than 6 times that. The diamond is the dominant cost. Thermal-grade polycrystalline CVD diamond in mid-2026 costs roughly $450 to $600 per square centimeter in low-volume custom orders. A standard accelerator footprint of 4 by 4 centimeters, 16 square centimeters, requires a diamond substrate of that area. At $500 per square centimeter, the diamond alone costs $8,000 per chip. This is not a component cost. This is a small car. The diamond cost is falling. It is falling for the reason Part 3 described in detail. The AI data center thermal boom is funding new CVD reactors, larger wafer formats, faster growth rates, and automated processing at a scale the synthetic diamond industry has never seen. The capital flowing into AI thermal infrastructure is paying for the manufacturing infrastructure that makes diamond cheaper for everyone. The trajectory: mid-2026, $450 or $600. Near term, 2029, $250, $320. Target crossover, 2033, $110, $135,000. At the 2033 crossover price of $120 per square centimeter, the diamond substrate for a 16 cm 2 accelerator costs roughly $1,920. Add the gallium charge, the tantalum barrier, the ceramic channel, and the MHD pump magnets, roughly $300 per chip, and the total cooling stack sits at approximately $2,220 per accelerator. Compared to the $350 copper and water cold plate, this is a premium of $1,870 per chip. This is where the argument turns. The $1,870 premium is not paid back by the cooling stack itself. The cooling stack is more expensive. It is paid back by everything the cooling stack eliminates. A traditional copper and water cold plate, at $350, is cheap at the chip. but it shifts a massive thermodynamic burden to the rest of the facility. The facility must provide industrial chiller plants to reject the heat the water carries. It must provide row-level fan walls to move air through the aisles. It must provide secondary water loops, pump stations, cooling towers, and raised floor plenum infrastructure. The power usage effectiveness, PUE, of a modern liquid-cooled AI data center sits around 1.25, meaning for every watt delivered to the chip, the facility consumes an additional 0.25 watts of cooling overhead. On a 100 kilowatt rack, that is 25 kilowatts of overhead, running continuously. The diamond gallium stack, by operating at the chip with a fluid of 6 times the volumetric heat capacity and a pump with no mechanical losses, and by eliminating the need for row fans and secondary facility loops, drives the PUE below 1.15. The 25 kilowatt overhead on a 100 kilowatt rack drops to under 5 kilowatts. The facility-side cooling infrastructure, the chiller plant, the cooling towers, the pump halls, the fan walls, the raised floors, is not merely reduced. It is, in the limit, eliminated. The elimination is the payback. A hyperscale facility deploying the diamond gallium stack at the chip level can delete the facility-scale chiller plant, the row-level fans, the mechanical pumps, and the secondary water loops from the building entirely. The capital saved on that infrastructure, and the operational power saved by not running it, pay back the $1,870 per chip premium. The payback period under continuous AI training load is under 14 months. This is the cost crossover. It is not that gallium makes the chip cooling cheaper. The chip cooling is more expensive. It is that the chip cooling, done correctly, removes the need for the building's cooling. The premium is paid at the rack. The savings are collected at the facility. And the crossover year, driven by the same diamond cost trajectory that Part 3 identified, is 2033. Act 6. The live front. A thesis is not a deployment. The integrated stack works in the laboratory. The thermal boundary conductance is measured. The cost trajectory is modeled. The payback is calculated. None of this means the architecture is built. The honest assessment of where this stands, as of mid-2026, is this. Liquid gallium magnetohydrodynamic cooling loops are at technology readiness level 3 to 4. That means lab-proven prototypes. Micro-machining fluid delivery. Cutting tool cooling validation. Academic demonstrations. It does not mean hyperscale production. It does not mean a supply chain. It does not mean a serviceable, field-replaceable cold plate that a data center technician can install and maintain. Direct-to-chip water cooling is at TRL 9. It is the default. It is shipping. The hyperscalers are building their facilities around it. The supply chain, copper cold plates, quick disconnect fittings, EPDM plumbing, manifold systems, is commoditized, standardized, and underwritten by a decade of operational data. Two-phase dielectric immersion is at TRL 7 to 8, with commercial deployments in specialized high-density clusters. Gallium is behind both. It is behind by years, not by months. The load-bearing assumption of the 2033 crossover is not merely that the diamond cost curve reaches 110. That curve is being bent by real capital expenditure, visible in reactor announcements, measurable in published scaling data. The load-bearing assumption is that the gallium loop scales from TRL 3 to TRL 8 in the same window. That scaling requires the tantalum and tungsten PVD coating pipeline to industrialize. It requires the ceramic microchannel manufacturing to standardize. It requires the hermetic sealing, inert gas blanketing, and oxide management protocols to become field serviceable rather than laboratory procedures. It requires a cold plate that a technician can install, leak check, and replace without a clean room. None of this exists yet. All of it is engineering, not physics. But engineering is the difference between a thesis that works and a product that ships. There is a second live front, and it is the one that recurs throughout this documentary. The tantalum barrier, the 50 to 100 nanometer layer that prevents gallium from infiltrating the diamond grain boundaries, is the single point of failure in the integrated stack. If the barrier delaminates, if a pinhole defect forms during deposition, if a thermal cycle creates a crack in the coating, the gallium reaches the diamond defects, enters the grain boundaries, and the spreader fails. This is the same interface problem that Part 1 named for the grid, the CTE mismatch that cracks the thermal path at the boundary. It is the recurring villain. It does not disappear because the materials are exotic. It reappears at every scale. The mitigation, the sintered silver nanopaste, the compliant interlayer, the accelerated life cycle testing, is real. Part 3 described it for the solar application. The same chemistry, adapted to the diamond to ceramic bond in the gallium channel, is the path to a bankable interface. But it is a path, not a fact. The 2,500 cycle accelerated test at -40 to 110 degrees Celsius, mapped through a Coffin-Manson fatigue model, gives a field equivalent cycle count that exceeds the service requirement with margin for solar in the desert over 25 years. The data center thermal cycle is different. It is faster, it is more frequent, and it is coupled to a corrosive liquid. The fatigue model must be revalidated for this application. It has not been yet. The final live front is scope. The 14-month payback assumes continuous AI training load. That is the load profile of the hyperscaler running frontier model training runs. The facility that runs at full power, 24 hours a day, for the life of the accelerator. That is the customer who can afford a $2,220 per chip cooling stack and amortize it against megawatt-scale operational savings. This architecture does not generalize. It does not serve the enterprise data center running mixed workloads at 40% utilization. It does not serve the colocation facility. It does not serve the edge. It is a hyperscaler-only play for the specific chips and the specific load profiles where the cooling infrastructure elimination is worth the per-chip premium. That is a narrow thesis. It is an honest one. Act 7. The synthesis. 5 industries. 1 wall. The wall is heat. In Part 1, we named it. In Part 2, we mapped the Rice University manufacturing unlock that made diamond available at industrial geometry. In Part 3, we followed the diamond cost curve into concentrated solar, paid for by the AI thermal boom. In this film, we followed the same curve into the building where the boom originates. The data center is where the wall is thickest. It is where the heat is densest, the cost of the wall is highest, and the incentive to break it is largest. The diamond heat spreader handles the first millimeter, the hot spot at the die, the phonon bottleneck at the chip. The liquid gallium transport loop handles the next meter, the convection of the heat out of the rack through a fluid of 6 times the volumetric heat capacity of water, pumped by magnetic fields with no moving parts. The two materials are not competitors. They are 2 halves of one thermal relay. Diamond is the sprinter. Gallium is the transit. The boundary between them, sealed by a tantalum barrier thinner than a wavelength of visible light, conducts heat by phonon-to-electron coupling at a rate 2 to 7 times faster than the diamond-to-water or diamond-to-copper interfaces it replaces. The integrated stack is not a bolted assembly. It is a single architecture, grown and machined and deposited and bonded, in which the heat never crosses a mechanical joint until it is already in the fluid that will carry it away. The cost crossover is $2,033. The diamond must reach $135 per square centimeter, a trajectory the AI industry is already paying for. The gallium loop must scale from TRL3 to TRL8, an engineering program that has not yet been executed. The tantalum barrier must be validated for the data center thermal cycle, a fatigue model that has not yet been run. The customer is the hyperscaler running continuous training load, not the enterprise, not the edge, not the colocation. If those conditions are met, the diamond gallium stack costs 6 times more at the chip and pays for itself in 14 months by erasing the rest of the cooling infrastructure. The chiller plant disappears. The fan wall disappears. The raised floor disappears. The secondary water loop disappears. The PUE drops below 1.05. The building that was a thermal engine that happened to compute becomes, finally, a building that computes. The wall does not fall because gallium is cheap. The wall falls because gallium is dense enough and diamond is cheap enough that the premium paid at the chip is smaller than the infrastructure deleted from the building. The material did not change. The manufacturing did. The architecture did. The same instrument. The same wall. The same originator. The diamond flattened the hot spot. The gallium evacuated the heat. The chiller plant disappears. The ceiling is cracking. Again. End of Part 4. Methodological Framework Statement. Dated July 19, 2026. This documentary extends the cross-sector thermal unification thesis, introduced in Part 1, June 28, 2026, into the data center thermal management domain. The argument that liquid gallium magnetohydrodynamic cooling loops, integrated with CVD diamond heat spreaders via tantalum or tungsten PVD barrier layers, represent a cost crossover architecture for hyperscale AI data centers at the 1,200 watt per chip heat flux regime, with a projected 2033 crossover contingent on the AI, subsidized diamond cost trajectory, and the industrialization of hermetic ceramic and barrier cold plate manufacturing, is, as confirmed by comprehensive review of academic, industrial, and journalistic literature as of July 19, 2026, an original synthesis. Intellectual priority for this specific integrated thermal stack cost crossover argument for the data center application is claimed by Richard C.J. Young, documented July 19, 2026.